There is a conversation that never happened. Two people who never met, who worked in different countries in different decades, who approached the same universe from directions so different that their methods looked, on the surface, like they had nothing in common. One of them built her career on abstraction, on stripping away everything specific and particular, until only the pure structure remained, the skeleton of mathematics beneath the flesh of calculation. The other built his career on the opposite impulse, on making the abstract visible, on finding pictures and stories and physical intuitions that turned equations into something you could almost touch. Emmy Noether, Richard Feynman. The same universe, two minds. I am Emmy Noether, and I want to tell you what Richard Feynman and I were both looking at from our different ends of the same telescope. Let me start with the thing that connects us, because it is not obvious and it took me a long time to fully articulate it even to myself. Most accounts of the history of physics present Feynman and me as operating in entirely separate domains. He in quantum field theory, I in abstract algebra, with different tools, different communities, and different vocabularies. And that is accurate as far as it goes. We never met. We never corresponded. In the ordinary biographical sense, we have no story together. But physics does not care about the ordinary biographical sense. Physics cares about the structure of the universe. And the structure of the universe turned out to contain something that connected our work in a way that neither of us, I think, fully anticipated. Both of us, in our different ways, were obsessed with the same question. Why does the universe have the structure it has? Not what are the rules. The rules can be written down, they can be checked against experiment, and they can be refined. But why these rules? Why should the universe be organized in a way that mathematics can describe at all? Why should the same abstract structures that a mathematician builds for purely internal reasons, following nothing but the internal logic of the subject, turn out to describe the physical world with terrifying accuracy? Before I can show you the connection, I need to tell you something about the way I think about mathematics that is not always well understood, even by people who know my work. Abstract algebra, the field I spent my career developing, is not about making things more complicated. It is about making things more simple. It is about finding the level of description at which the essential structure is visible without the surrounding noise. When I defined a group, or a ring, or a field, I was not adding complexity. I was removing it, stripping away everything that was specific and contingent until only the logical skeleton remained. The skeleton was the thing. Everything else was decoration. This question has no final answer, but the partial answers we found, Feynman from the physical direction and I from the mathematical one, turn out to be, in a very precise sense, the same answer approached from opposite sides. Start with my side. The theorem I proved in 1915 says this: every continuous symmetry of a physical system corresponds to a conserved quantity. If the laws of physics are the same at every moment of time, if nothing about the rules changes as time passes, then energy is conserved. If the laws are the same at every point in space, if the rules here are identical to the rules there, then momentum is conserved. If the laws are unchanged under rotation, if it makes no difference which direction you call north, then angular momentum is conserved. The symmetry and the conservation law are not merely related. They are the same thing, expressed in two different mathematical languages. This was not obvious when I proved it. It required a sophisticated piece of mathematics called the calculus of variations, applied to the abstract formulation of mechanics that Lagrange and Hamilton had developed in the 18th and 19th centuries. The proof was technical. The result was not. The result said something about the deepest structure of the physical world, that what is conserved in nature corresponds to what is symmetric in the laws, and that these two things are not independent facts, but a single fact seen from two angles. Feynman, 40 years later, was working on a completely different problem. He was trying to understand quantum electrodynamics, the theory that describes how electrons and photons interact. The equations were known. They worked. But something about them was ugly. The infinities that appeared when you tried to calculate certain quantities, the answers came out infinite, which is not a physical answer, suggested that the existing formulation was hiding something, that the way the theory was written was not the deepest way to write it. His solution was to reformulate the entire theory in terms of a new object, the path integral. Instead of describing the quantum state of a particle at each moment and calculating how it evolved forward, he asked, what if you summed over all possible paths a particle could take between 2 points? Not just the classical path, the one that minimizes action, which is what classical mechanics tells you a particle follows. All paths. The straight path, the curved path, the path that goes backward in time for a while, the path that visits the moon on the way to the laboratory. All of them, each contributing an amplitude, and the total amplitude, the sum over all paths, gives you the quantum mechanical probability. This sounds insane, and the first reaction of most physicists who encountered it was that it was insane. But Feynman could show that his formulation was mathematically equivalent to the existing formulations. It gave the same predictions, and it described the same physics. The difference was not in what it calculated, but in how it thought. And how it thought turned out to be enormously productive. There is a moment in Feynman's development of the path integral that I find particularly illuminating. He was trying to understand a formula that his supervisor, John Wheeler, had shown him, a formula that seemed to suggest that the action of a system determined its quantum mechanical amplitude. Feynman did not know at the time that this was a deep connection. He thought it might be a trick, a useful shortcut, but he followed the mathematics wherever it led without requiring it to make intuitive sense at every step. And what emerged was the path integral formulation, a complete rewriting of quantum mechanics in terms of the action principle. The same principle that my theorem had identified as the key structural element 40 years earlier. Here is where Feynman and I come together. The path integral formulation is, at its foundation, a story about action. The quantity that you sum over all paths is the action, a mathematical object that encodes the dynamical content of a physical theory. And action is exactly what my theorem operates on. The Noether theorem is a theorem about the symmetries of the action. The conserved quantities that the theorem produces are derived from the action. The entire framework in which my result lives is the framework of the action principle. The idea that the laws of physics can be expressed as the statement that physical systems evolve in ways that make the action stationary. Feynman took that framework and quantized it. He made it the foundation of quantum mechanics rather than classical mechanics. And in doing so, he showed something that my theorem had already hinted at. The action is not just a calculational convenience. It is the most fundamental way to describe physical law. It is the level at which the deepest structure of physics lives. My theorem says symmetries of the action produce conservation laws. Feynman's path integral says quantum mechanics is a sum over paths weighted by the action. Both of us, working from different directions, were pointing at the same object, the action. The most abstract, most general, most powerful way of writing down what a physical system does. But I want to go further than this formal connection, because there is something deeper here about the relationship between mathematics and physics that I find genuinely important and that is rarely stated clearly. Feynman was famous for distrusting formalism. He was suspicious of abstraction for its own sake. He wanted to understand things, really understand them, in the sense his father had taught him, which meant being able to see what was actually happening rather than just being able to calculate what would be observed. He developed his diagrams, the Feynman diagrams that every physicist in the world now uses, because he needed a way to visualize the terms in a perturbation expansion of the path integral. He drew pictures of electrons exchanging photons, not because the pictures were literally accurate, they are not, but because they organized his thinking and gave him physical intuition about which terms in an infinite series were important and which were negligible. I had the opposite instinct. I stripped away the pictures. I wanted the pure structure, the relations between objects without the objects themselves. My approach to algebra was to define structures by their properties rather than their representations. To say, here is a set with these operations satisfying these axioms, without ever asking what the elements of the set look like, or what the operations do to specific things. Abstract algebra, in the sense that I developed it, is the systematic study of structure in this form. But here is what I have come to believe, looking back across both of our careers. Feynman's pictures and my abstractions were not in competition. They were not different philosophies of mathematics or physics that happened to arrive at some of the same results. They were complementary tools for accessing the same underlying reality, each capable of revealing things the other could not see. Feynman's diagrams made visible the physical content of calculations that would otherwise be opaque sequences of symbols. When you draw an electron emitting a photon that is absorbed by another electron, you can see what the calculation is about. You can see that higher-order diagrams, loops, more complex interactions, represent physical processes that are happening simultaneously and must be included in the calculation. The picture tells you what you are calculating before you calculate it. This is enormously valuable because it allows physical intuition to guide mathematical work. My abstractions made visible the logical structure of relationships that would otherwise be buried in specific calculations. When I defined a group, a set with an operation satisfying closure, associativity, identity, and invertibility, I was not describing any particular group. I was describing what all groups have in common, the property that makes a group, rather than some other kind of mathematical object. And once you see the structure, you see it everywhere. The symmetries of a square are a group. The symmetries of a sphere are a group. The symmetries of the laws of physics are groups. The same abstract object, in infinitely many specific instances, each illuminating the others. This is what happened when my theorem met Feynman's framework. The abstract structure I had identified, symmetry producing conservation, turned out to be exactly the structure that the path integral needed in order to be renormalizable, in order for the infinities to cancel, in order for the quantum field theories that Feynman was developing to be mathematically consistent. The gauge symmetries of electromagnetism and the other forces, the symmetries that Feynman's approach naturally highlighted, are precisely the continuous symmetries to which my theorem applies. The conservation of electric charge, which is the thing that makes electromagnetism work, is a consequence of a gauge symmetry of the action. My theorem, Feynman's framework, one result. There is something I want to say about the difference between our personalities, because I think it illuminates something important about how mathematical and physical understanding develop. Feynman was enormously impatient with formalism that he could not immediately connect to physical reality. He once said that he could not understand something until he had a physical picture of it, that equations without pictures were not understanding, they were calculation. This is a genuine and important view. It produced the diagrams, it produced the path integral. It produced an ability to solve problems that no one else could solve by working from physical intuition rather than formal manipulation. I was the opposite. I was impatient with physical pictures that obscured the mathematical structure. I wanted to know why a result was true, what abstract property of the system was responsible for it, not merely how to calculate it. My most important theorem came from noticing that the proof of conservation of energy and the proof of conservation of momentum were both instances of the same abstract argument, the same structure appearing twice. Once you saw the structure, you could see it everywhere. Once you abstracted the argument, you could apply it to any physical system described by an action principle, which turns out to be all of them. I want to tell you about a specific moment in the history of physics where this connection became explicit, because it shows the power of having both approaches simultaneously. In the 1950s and 1960s, physicists were trying to build a quantum field theory for the weak nuclear force, the force responsible for certain types of radioactive decay. They knew the force existed. They had data about its effects, but every attempt to write down a consistent quantum field theory for it ran into the same problem: infinities that could not be renormalized and mathematical inconsistencies that meant the theory broke down at high energies. The resolution, which came gradually through the work of Glashow, Weinberg, and Salam, was to recognize that the weak force was part of a larger structure, a gauge theory based on a specific symmetry group. The symmetry was not obvious from the experimental data. It was hidden and spontaneously broken by the Higgs mechanism in a way that made the weak force particles massive and short-ranged, while the photon, the carrier of electromagnetism, remained massless and long-ranged. But the underlying symmetry was there, and once you saw it, the infinities cancelled. The theory became renormalizable. The mathematics became consistent. This discovery unified the electromagnetic and weak forces into a single framework, the electro-weak theory. It was a triumph of exactly the interplay I am describing. The symmetry approach, the Noether approach, told physicists what structure to look for. The path integral approach, the Feynman approach, told them how to calculate what the structure predicted. Together, they produced a theory that has been tested against experiment to extraordinary precision and found to be correct. The same story repeated itself with the strong nuclear force, which holds quarks together inside protons and neutrons. Again, a hidden symmetry, this time a color symmetry among quarks. Again, a gauge theory. Again, the Noether structure and the Feynman calculational machinery working in tandem. And together, the electro-weak theory and the theory of the strong force form the standard model of particle physics, the most precisely tested theory in the history of science. Everything we know about the fundamental forces of nature, everything except gravity, which remains stubbornly outside the standard model, is built from this combination. The abstract symmetry structure that my theorem connects to conservation laws. The physical calculational machinery that Feynman's diagrams and path integrals provide. Two approaches to the same reality, discovering that they were always describing the same thing. Feynman once said that the thing he found most remarkable about mathematics was its unreasonable effectiveness. This is a phrase coined by Eugene Wigner. Why should mathematics, developed for purely internal reasons by people following purely internal aesthetic criteria, turn out to describe the physical world? It is not obvious that it should. It seems, on the face of it, like an enormous coincidence. And yet it keeps happening, with a consistency that suggests the coincidence is not a coincidence. I think I know part of the reason, not all of it. The question is too deep for a complete answer, but part of it. The reason is that the physical world is, at its most fundamental level, a world of structure and symmetry. The things that are true about the universe, the conservation laws, the forces, the particles, are not arbitrary. They are the way they are because they are the simplest structures consistent with certain symmetries. The universe is, in some sense, the most symmetric thing it could be while still containing anything at all. And symmetry is exactly what mathematics is best at describing. The unreasonable effectiveness of mathematics in physics is less unreasonable once you realize that both are, at their cores, the study of structure. Feynman saw this from the physics end. He noticed that nature was always elegant, that the right theory was always simpler and more beautiful than the wrong one, that when calculations became ugly and complicated, it was usually a sign that you were working in the wrong framework, and that finding the right picture made everything clear. He trusted beauty as a guide to truth, not because he was being mystical, but because he had repeatedly found empirically that it worked. I saw it from the mathematics end. I found that the most abstract structures, the ones that seemed most disconnected from any physical application, turned out to be the ones that described the deepest physics. Lie groups, which I and my contemporaries developed as purely mathematical objects, turned out to classify all possible gauge symmetries of physical theories. Representation theory, which studies how abstract groups can act on vector spaces, turned out to be the mathematics of particle physics. The mathematics arrived before the physics needed it, as if the universe had been waiting for the tools to be built. Two people, two methods, two different ways of insisting that the world has structure, that the structure is beautiful, and that finding the structure is what physics and mathematics are for. Feynman said once that if you want to understand nature, you have to be comfortable with abstraction. I said, in various ways throughout my career, that if you want to understand abstraction, you have to eventually find the concrete reality it describes. We were, I think, both right. And we were, I think, saying the same thing. The universe has a language. It is neither the language of diagrams nor the language of abstract algebra exclusively. It is the language underneath both, the language of symmetry, of conservation, of the deep structural reason why things are the way they are and not otherwise. Feynman drew it, I abstracted it. The universe wrote it. And we were both reading the same page.